Okay, we have today a talk by John Chi, and he will talk about mixing and stratification within the plume of the Changjiang River, estuary, East China Sea, a numerical model.
Hey, good morning. Thank you very much indeed. Before my talk, I wish to thank Newton for having inspired me in many ways. And in terms of my mind, I would say my mind is below the average of intuitive mathematics as defined by Blaise Pascal. And it's my great pleasure to present you an overview of mixing and stratification within the plume Changjiang River estuary, which is part of the East China Sea, which Li Feng and I are still learning because it's a very, very complicated topic. An outline of my talk, you can see 4 parts. The first, introduction, and second, the mathematical model, and the third, results. I subdivided into the 2 parts. Then finally, a very brief summary. And as you know, the Earth is an ocean world, and the studies of the plume have been of interest, I think, to the coast engineer, coast oceanographer, and the environmental fluid dynamics all over the world, I would say. But the next slide would show and to my best knowledge, a Scottish scientist, John Fleming, in 1860, first identified the salinity stratification in Tay estuary. And since then, numerous studies have been undertaken worldwide. Okay, that's the slide showing the historical overview. And for the Changjiang River estuary, I think this is the earliest Chinese literature, 1963. And as you can see, including my group study, we're still working on I try to learn the physics. Okay, we're using very simplest mathematical tools, right? And I'd like to show you the time series of the field data. As you can see in the middle part, those 3 panels do show suggest the salinity displays the strong flood appetite variability, very, very strong stratification. Okay, I think that's the motivation of my study. And in terms of the physics, I think first I'd like to present you some very conceptual physics. Some of you know a lot about the physics of mixing, but in the estuarine and coastal waters, we constrain our studies to what? To the mixing caused by the generally shear production and the buoyancy production. I don't think I can talk all those relevant processes. I think I would focus on the wind stresses and bottom stresses for shear in production. And I think that's it. Okay, and in the estuarine coastal waters, another associated process is mixing, and I think the stratification are what? I use the word verse, okay, and those are the processes. As you can see, to mix the water, the column, the kinetic energy has to be converted to potential energy. Then the mixing increase the potential energy of the water column. This is the conceptual diagram showing how they are interacted. Okay, how they're interacted between the mixing and the stratification. I think I'm particularly interested in some circulation, of course, tidal straining as well. And okay, and so those two the conceptual sketches showing the physics. And in my view, the terms, the physical understanding definition of the mixing and the dispersion are still debating. Well, I quote Ron Smith, his view of what's the mixing, what's the dispersion. I'm not going to read it in detail. Well, the area we are studying is one of the largest river. It's called, where the chairman pronounced it very correctly, Changjiang River, means long river, actually. Well, in terms of the regional significance, well, it has the physical, engineering, biochemical, and ecological environment. But generally, the concerns over the water quality and the ecosystem, I think this is the major motivation. Right, and I'd like to show you the very update, the river discharge of Tong River. As you can see, very strong seasonal variability. This is dry season. This is the flood season. You can see the magnitude of the discharge. And okay, this is also a very updated wind rose direction diagram. As you can see, what in generally in the Changjiang River estuary in the winter, in the dry, so-called in the dry season, northwest wind would be the prevailing wind. Right, and the overall objective of this study, well, I use the study again because it's very, very hard to understand, but we try to learn. So we try to learn mixing versus stratification within the plume of the Changjiang River estuary, and to understand the fundamental forces, primary forces, driven by four tidal constituents and what? Under the action of combined tidal constituents and the prevailing, okay, and in the flood season and the dry season and the steady winds. Well, in the flood season is southeast, direction, and during spring tide in the flood in the flooded dry seasons, respectively. Well, the model we used is, I think some people might know this. It's called coherence, but we have improved this model because the original the grid is rectangular, right? And well, those are the primitive equations on mathematical physics, where you can see the continuity equation, momentum, and pressure and salinity equations, like other ocean models. And also, like all ocean models, so-called model splitting technique has been used for coherence. And from this, this diagram, as you can see, so-called model splitting technique. Well, I'm still trying to understand this because I'm asked by many people, what's the 2D? Well, 2D external mode, but from this cartoon sketch you can see is what? Is depth averaged. And this is the 3D internal mode. Okay. And well, you can see the location of arrival on the sigma coordinates. Well, the sigma coordinate transformation, it is necessary in order to dealing with the bathymetry, the complex bathymetry. And in this study, 10 sigma layers have been used. Okay, this is the before transformation. This is after transformation. And it's nice for me to show you what Changjiang River estuary looks like in terms of the 3D relief map. As you can see, it's very, very complicated. Okay, especially how they would affect tides and those physical processes. I think it's very, very complicated. And okay, as I said, we try to improve because of the geometry and the bathymetry complex. We have to improve. The improvement has been made to coherence using so-called orthogonal curvilinear coordinate transformation to cope with complex geometry and bathymetry in the estuary, in the Changjiang River estuary, or maybe other estuary as well. And this is the cartoon sketch showing the transformation. And and after orthogonal curvilinear transformation, the grids, that's for the whole computational area, Well, the boundaries we set actually based on the field measurements. Field measurements means we knew the extension of the Changjiang River plume. Then we extended a bit further eastward, southward, and northward. Okay, but the computation area is too small compared with your computational domain. And as you can see, 149 times by 69 grids have been generated, and the grid cells dimension range. The minimum is 280 meters to 5,583 meters. I think very fine compared with at the most ocean, large-scale ocean model. And this is the diagram showing the square computation grids after orthogonal curvilinear coordinate transformation. And one unit refers to the each grid step. Well, this slide I'd like to show you after orthogonal curvilinear grid and those primitive equations. They've transformed in those forms, continuity and momentum and salinity. I think it's a bit complicated for me. And this is for the 2D external mode on the orthogonal curvilinear grids. Okay, the primitive equations are transformed on the orthogonal, but this is for the 2D external equation. Well, I'd like to draw attention to, in fact, those two modes, are closely linked as the barotropic pressure gradient calculated with the external mode is generated prescribed to the internal mode. So this is how they work together. Then, in terms of time steps, to satisfy the CF error condition, those are the time steps we used. For 2D external mode, 5 seconds, and for 3D internal mode, 150 seconds. Very conventional total variational diminution scheme has been used for the convection term in the momentum in both momentum and salinity equations. In terms of the turbulence closure model, we used is the K error model. We found the K error turbulence model would give us that more stable condition when we model the plume. And well, so this is the top line is a KR model. The bottom part, well, in order to calculate the vertical eddy viscosity coefficient, the momentum and the scale equation, we simply use Mel and Yamada. But they have been those, well, this is the original equation, the page number, but they have been transformed on the Austrian curvilinear equation. That's the equations after transformation. And well, another important parameter, another two important parameters, the horizontal components of first eddy diffusivities and second viscosities. But we use a small log risky equation 422 page 105. Yeah, I think I like this kind of citation for the clarity. And then those the transformed equation on the Austrian curvilinear gray. Okay. Well, those are the equations we calculate horizontal components of eddy diffusivity and viscosity. And the DG is the deformation velocity tensor. Then in terms of boundary condition, well, I list partially here. Well, I specify the year 2002 simply because after 2002 there is larger hydraulic engineering project. It's called Three Gorges. Dam was constructed, right? And so this is the year, right? Before that, we used the mean value of river discharge over last, I think over about 50 years. We got this 49,500 per second cubic meter per second for the flood season. Then for the dry season, it's 400 cubic meters per second. Okay, then this is the salinity. And those are the initial conditions. And well, two modeling cases we run. First, without wind. Okay, with wind. With wind, then the surface stresses would have to be taken into account using this equation. Okay, the bottom condition. This is I think is very, very conventional equation. Right, then there's also this is the open boundary condition. Well, this open boundary condition is what for the two external. Well, what I meant by open condition is open boundary is the tides, okay, the incoming tides on the east, right? And this is the 3D internal. The open boundary condition for the straight. Right, and very brief introduction to the physics of stratification. Again, I'm still learning this, right? But well, this is a sketch showing, you see, how the so-called potential energy anomaly would be generated, okay, from what? Yes. From this, then to this. This is the phi. Well, we simply adopted Jiao H simplest equation. Well, this is the stratification. Well, we defined it. We use this to evaluate whether the Estuary waters have been stratified or not in the Changjiang River estuary. Right, I would like to nod to the Born-Jeans for tides. And let's move on to the results part. First part, I think, is validation of the model. We have to validate. I think it found basically three. First, we have to. Well, those are the computation domain, and well, we need a lot of field data, but well, those are the hydrologic station for validation we could have. Okay. we have done our best. And the tidal station, the gauging station, okay, those the where they are where they located. And well, this is the first part. Well, I think 4 tidal constitution, M2 tide and S2 tide, K1, S1, would be sufficient, okay, to model the tides in the Changjiang River estuary. But we would like to take more tidal constitution into account in the future. And well, this diagram shows 4 players shows the validation for 4 tidal constituents. Those solid lines are the model. Yes. And then okay, no. The solid line is a co-tidal line, okay, and the dashed line is iso-amplitude lines. Well, they have been validated against the measured data. Okay, I think they are in fine, reasonable agreement. And the second validation we have made for tidal elevation, current speed, and current speed and the direction. Okay, and the direction. But you can see there's a reasonable agreement between the model results and the measured result. Right? And the third is validation for salinity. Well, I have to speak very cautiously, because it is very hard to validate the salinity. But in terms of the mixing and stratification process, we would have to. So I select one. I think you can see this one quite a nice agreement between the model and measured salinity. So after those validation, and we can run our model, and we would assume the model results would be accurate, right? And I think the first part I'd like to present very briefly without wind, tidal effect only, and those are the 2 animations. Well, top panel is I think it's for the flood season, and the bottom is for the dry season. Well, I think you can see from the animation how the plume is being, first how the buoyant plumes look like, and how they are formed, and then third, finally how they changed. Okay, under the action of 4 tidal constitution of the tides, without wind. Okay, without wind, and also you can see the strong seasonal variability, flood season and dry season. Okay.
What
What
are we looking at here? We're looking at salinity, just some vertical average, or what is it?
You mean the salinity value?
Well, no, but I mean, is it an integration over the depth, or is it some?
I would say it's that integrated value. Yeah. Not just the surface, not the bottom, not the middle part, not the depth integrated. Well, I should have specified this. So be clear?
Is there some sort of outflow condition specified, such that, so you've got the fresh water coming in, which I would assume there's a boundary condition, that the flux of fresh water.
Yeah, the blue color is more fresh water.
And it comes and mixes with the water in the sea.
Yeah, that's right.
And are there some of the boundary conditions such that it can also flow out of the domain in the sea area?
I would think so, but this is the computational domain we currently use.
That's quite hard, right? I mean, no, Herben de Boer, who was Julie Petrusak's student, had absolute hell attempting to convince a river plume to leave the domain without bouncing off the wall. So I'm kind of interested as to how you made that work.
You mean
so when the plume
the boundaries will be constrained?
Because the plume's exiting clearly at the bottom left, right? So you have, especially in the flood season case,
Yes.
the plume's going to come out, it's going to turn right, and it's going to go down the coast, and you can actually see it doing that. So therefore, the plume must be exiting at the bottom left-hand corner along the coast. And actually convincing a model to do that is quite hard, so I'm quite impressed. It's really actually going out there.
But I think we made a qualitative comparison with, between these with some even field measurement and satellite image qualitatively okay, especially as you mentioned the spreading direction.
I mean, it looks alright. It doesn't
Yeah,
look like
so
it's picking up at the exit. So,
Okay. But it is consistent with observation data. So we are convinced the model is okay, right? Good enough. And well, to quantitatively understand how the plume increase through the time, we select the lens called a plume lens, and we plot the time series of the Changjiang River plume lens, and then compare the surface elevation, top lens flood season and dry season. I think you can see how the fluctuated through the time corresponding to those surface elevation. I think this is semi-quantitative. And then to better understand, the features, the processes of the plume, well, we select some snapshots from the animations. Well, I like to explain this. Well, see, on the left column is a flood season. Okay. So on the right is the dry season. Then the top four refers to springtime, and the bottom four refers to nip time. Okay. Then, yes, for each four, then this is the flood, and ever, flood, ever. So our aim is to try to understand the first time scale, the seasonal, the second, spring nip time, third, flood and ebb time, and how those plumes would change. Well, I think from those snapshots we can see the striking features. Well, if you look at the shape and compare with these, they are. But I specified two here, the jet flow, right? Jet flow, and this is probably in the literature is being defined as a circulating barbarature. Okay, those are the very nice features in the plume. Okay, and I think this would apply to the water tangle. Those are the features. From these three, those plots, we can see how they varied seasonally, nip tide, and flood ebb tide. And this is for the upper part. Okay, upper part. We subdivide into the buoyant plume, the upper part and the lower part. This is for the upper part, and the next is for the lower part. Okay, the lower part of the buoyant plume. And and I also I'd like to draw your attention to how the stratification parameter has been distributed in this area, in this so-called freshwater influence area. Well, again, on the left is for the flood season, on the right is for the dry season, and you can see. But generally, stratification is stronger in flood season than the dry season. In the dry season, I would interpret it, there is just no stratification, okay, or not significant. I think more significant. Well, so this marine ecologists are very interested in. They would think those, the higher the stratified waters, the reptiles might walk, but I have no idea. I'm trying to learn the physics. Right. This is the stratification.
Can you explain what this parameter is, please?
It is stratification parameter.
Or what is it? Is it phi that you defined before, or?
We use the. I did show you. Yes.
This quantity here.
Yes. Phi is a stratification parameter used.
So it has units of energy density. So I guess it's the
Yeah.
the available energy due to stratification. I
Right.
guess.
I don't think I can answer the question, but this is the parameter we use, okay, for estimating whether the water is stratified or not, or how strong is it stratified.
So the reason it appears to be away from the river on the left-hand side, out into the sea, is because the river itself is not stratified. Is that what you're saying? And so that's the zone where you're transitioning from fresh water to salt water, basically. Is that what we're seeing?
Well, my understanding in the flood season, the plume would be more strongly influenced by the river discharge.
Sure.
Because more river. In the dry season, less, right? Is this a reason for what? For those smaller stratification parameter in the dry season? Okay. And this is I'm interested in excellent circulation, so we plot those longitudinal cross section, as you can see there. Yes, there is apparent type excellent circulation. And another interesting, I think it's interesting, we plotted the different kind of energy. And for the flood season, dry season, spring tide and neap tide and flood tide and ebb tide. Our interpretation is there seems to be an hysteresis in moderate turbulent kinetic energy, which is consistent with those studies available in the literature. Okay, this is the diagram. And this is a very brief findings of the part 1. And I think, as I highlight here, the 2-layer and the saline strategy appears to be controlled by the tidal mixing, estuary circulation. Those are the two main. And the stratification does display a season of fortnightly tidal variability patterns, especially stronger in the flood season than in the dry season. And weak during the springtime, and then the neap tide, and stronger at the maximum flood tide and at the maximum ebb tide. Okay, the next one I'm going to move on to. Yes, so-called combined effects of tide and wind. Okay, then again, two animations. Well, this refers to the flood season, where the prevailing wind directions is south-southeast direct, I guess, easterly, and dry season prevailing wind is northwest. Well, yes. So, I'd like to draw attention to this. The output now. You can see the fresh water. Maybe you can use the word patches. Well, there could be two. You see, one is very, very eastward, all right? And so there are two parts. Those are the, well, we submitted the paper, what we said are quite interesting features from the model design. But we try to understand what mechanisms. You see, but in the dry season, no, there's no. Well, generally, simply, wind would, but a strong effect, the spreading of the river flow in the Changjiang River estuary. Okay, these are the two animations. Again, we try to quantitatively understand how fast the river plume would grow through the time, and we plot those. I think it was this dry season. You can see how the there's the time series from all the Changjiang River plume bands, and compared with surface elevation. And the T1, T2 are specified for the times. T1 prime, T2. At those two times, then we selected the snapshots and plotted those. Then again, left column flood season, right column the dry season. Then up for spring tide is the lower for neap tide. Then again, flood tide, ebb tide, flood tide, ebb tide. I think the striking features, as I mentioned, the freshwater patches, you see, spreading eastward, and under the combined effect of the tides and wind. If we compare these with those tided only, and they're quite different. So the wind do again impose on the effect on the plume spreading. But in the dry season, you can see this is probably because of the less river discharge in the right. And this is for the upper part of the buoyant plume, and this is for the lower part of the buoyant plume. I think we can see the extension of the plume. And and this is the stratification parameters. The horizontal distribution of the stratification parameter in the flood season and dry season. Again, we'll see stratification is stronger than, much stronger than in the dry season, and those areas are highly stratified. Okay, in other words, larger stratification parameter 5, and we compare those values with those tides only. Those stratification parameters could increase 20 or up to 80% more.
Also seems to go a lot further offshore.
Yes.
And it goes offshore, slightly counterintuitively for me, it goes offshore in the upwind direction. This is kind of surprising.
I didn't get your point, did you?
So the area of the plume is big enough
Offshore,
wind on, but it's not bigger it doesn't get blown downwind. If
But
anything,
I don't know
it goes
why.
upwind.
But I don't know why. But those are all calculated results. Yeah. Okay.
But what happens to the overall circulation pattern when you impose winds, even if you don't have a river flow?
You mean
Just
horizontally or vertically, or longitudinally?
If you just calculate the surface wind patterns, the surface currents,
Surface currents.
without without
Those
the
are the-
river plume? What happens to that when you impose winds on it?
Well, those are the velocity vectors. Well, the wind, as I said, we assume as a constant. Sorry, steady wind. Simply add the wind stress.
But you have rotation in this system, right? So you must have some Ekman
Yes.
pumping or something, pushing it.
I think we should take the rotation into account.
So essentially, you are looking at the freshwater lens, the thickness of the freshwater, and to study probably the marine ecological systems like chlorophyll growth and plankton, etc. The purpose of the study.
No. I said that those results are of interest to those marine ecologists.
Okay.
Because the highly stratified waters where the red tides frequently occur. But I have no idea. This is what they told me. But I'm just trying to understand the physics. But it's still very hard. Okay, those are the cross section.
So instead of you are taking a vertical like integral over the column for the both the density and the salinity, right? Rather than that, like if you take a vertical profile.
Well, I'm interested in the circulation. Try to understand how the tidal circulation would affect the mixing stratification. Okay, but maybe in the future I should take the density. You said the density, right? Into account. And again, we interpret. We found there seems a hysteresis of turbulent kinetic energy, dry season, spring tide, neap tide, and flooded ebb tide. And even under the combined tide and wind, the combined effects of tide and wind. Okay, this is the brief findings of part 2. Well, generally the wind direction would yes the stratification or destratification, or I did not specify destratification, small stratification parameter. Okay, and within the Changjiang River plume appears to be controlled by the direction of the different prevailing winds. And as I said, the stratification parameter could increase back to 20 up to 80% more than without wind in the flood season. And this is another finding where the upwelling favorable wind drives plume to disperse seawards and tends to enhance the stratification, where the downward favorable wind drives the plume to move landward and causes destratification. And finally, there is apparent hysteresis in the model of turbulent kinetic energy. The next 2 slides I would like to show you what we are currently doing. Well, apparently the meshes will have to be refined, and so this is the preliminary. So we use a finite element method, so-called triangular grids. So try to refine the computation of grids.
Whose code is this?
Sorry?
Is this did you write this code or is this one of the
No,
other
we
ones?
use the Telemac.
Telemac, okay.
Yeah, Telemac. Well, it's a free download. Right, yeah. And second, finite volume method. Okay, finite volume method with the extension of a computational domain. There are 2 largest estuaries near Shanghai where I work. Another one is Hangzhou Bay. We think we just cannot cut this. So in the currently we are working on this. So maybe we can. Well, next time I can show you more interesting results. And those are the conclusion. I'm not going to repeat. Okay. And finally, I would like to thank you very much indeed for your coming.
The questions.
Come back to the question of the spreading of the stratification. Do you have the Coriolis terms in your governing equations? I missed them.
I would think so. We use the. I think use how to let me. I think in the equation is the Coriolis parameter f. It is
okay.
taken into account, right? But
We'd have to mean 30 degrees. Still a pretty significant number, particularly in the root window.
yeah, f equals omega sine. We go back to the equation. No, maybe I did not type it on the slide.
Yeah, it's there. If you go back, go forward 2 more. They were there.
This one?
Go forward now.
Yeah.
Yeah,
Oh, there is f here.
Oh, there they are. Right, thank you.
Yeah.
Yeah. Yeah. But Paul's, you're suggesting the question about rotational, like a Rossby number, we have not calculated. Do you think we should calculate the Rossby? The flow is definitely rotational.
I thought you made the point in your conclusions that upwelling and downwelling play a role in this system, and that's clearly a rotational effect, right? I mean, so the influence of taking the flow away from the coast is associated with the Coriolis term taking the fluid at the surface away, right, and bringing the fluid up from below. So that's presumably why you're seeing some eastward spread of your plume in that situation.
Okay, yeah, I realized that, but since I came to them, I realized that this should be taken into account, the rotation.
Further questions? Okay, then let's thank John again.
Okay, thank you very much indeed.